No, it looks like it's 10 a.m., so why don't we jump right into it? Thanks so much, everybody, for joining. If you're watching us on YouTube, please hit that subscribe button. It really helps our channel grow and helps more people learn. Today, we have Graham Stevens joining us, as well as his cat in the background. So glad that your cat could be here. What's your cat's name again?
Katrina.
Katrina. Very rare to
Yes.
have a orange female cat, but thanks for joining, Katrina, and as well as everybody else on the call. Today, we're going to be talking about HFSS. On the next slide here, I have a poll question for you guys. I've been asking this the past 2 sessions. I just want to know how you guys found out about today's session. Did you get this email on the right? Did you use the Zoom link here to find out what today's topic was going to be? Did you find out on social media, the KETIV website? Let us know. We're working on a few new newsletters. So next week, you will not receive the email on the right. You will instead receive a monthly newsletter with all of the topics listed. We'll also have all of the replays listed in that email as well, but we're moving to more of a monthly newsletter form. That way we're not sending you a million emails, and instead you'll receive just the email on the left here. So be on the lookout for that. It's not nothing too crazy. And at the end of the session today, you'll get a survey. There'll be a survey link at the end of the session. So if you have very strong feelings about this email, please let us know. We'd love to know your thoughts and how you're receiving information and learning about new topics. You can also let us know topics that you would like to see covered in that survey. Okay, I will let Graham kick us off and get the webinar started. Thanks for joining, everybody.
Alrighty. Thank you so much. Hi, I'm Graham Stevens, an application engineer here at KETIV, focused on ANSYS, and in particular, high frequency, low frequency electronic applications and optics. And today, I'd like to kind of describe different HFSS antenna approaches, in particular focusing on the latest one, which is called 3D component array domain decomposition. And we'll be going through what these different antenna approaches are, when you might use one versus the other, and then how do we do setups for each of these. And then some tips and tricks relative to speeding up your antenna simulations. And sort of comparing all these different methods and what sort of computational resources they might take, as well as accuracy. As we go through this, of course, we're focused on trying to get the absolute best out of your hardware configuration and speed up your antenna design work. So that's the focus of today's webinar. And so this slide here gives a broad overview of these different antenna array approaches. On the left, we have the unit cell infinite array approach. And in this approach, we take a unit cell for the antenna and we assume that it goes off to infinity. And given that assumption with that infinite periodicity boundary condition, we can mathematically calculate the array factor to get an approximate finite array pattern, but we neglect edge effects. Yeah, so it's slightly less accurate, but it's also much faster because we're just doing one unit cell as opposed to multiple unit cells. Kind of off to the right, the far right, is our explicit finite array here. And this is where you have the antenna array and you simulating it explicitly. And so you have each individual unit cell explicitly modeled. You can have non-uniform array elements. You can have any geometrical arrangement of the elements. So you're not restricted there, and it includes edge effects and everything that you might want in terms of the output, but it also takes a lot more time and is computationally more intensive. HFSS tends to be RAM limited, so you can get to the point where you're running out of RAM or your model is too big for your machine. And then in between these two, we have something called finite array domain decomposition, which essentially simulates an identical unit cell. It assumes that we have a finite array now. In this particular case, it looks like it's a 7x7 array. And each of those elements are identical, or assumed to be identical, but it is a finite array. And in this case, we now can account for the edge effects, but instead of modeling each individual patch explicitly and having additional mesh and additional computational time needed, we're only meshing and doing computations on one unit cell. And as a result, you can go much, much faster than the explicit array. And the results are pretty darn similar. They're very, very close. And then similarly, so the latest iteration and configuration of this is called 3D component array domain decomposition. And this allows you to avoid every unit cell has to be the exact same restriction. Now we can have unit cells where maybe the inside unit cells are all the same. Maybe some of them are rotated relative to each other. Maybe you have side pieces that are slightly different or corner pieces that are different. And you can model those individual differences with individual unit cell blocks. But you're still only, you're still taking advantage of the available repetition and reducing the total amount of computation needed compared to the explicit finite array by quite a lot. And this includes edge effects. It's very similar. It's enabled by mesh fusion. Each of these individual blocks are basically sort of stitched together using the new mesh fusion technology. And again, it allows you to get much faster results compared to the explicit finite array, enables you to handle much larger arrays as well with less RAM, and your edge effects are included, and accuracy is pretty high compared to explicit. So that's a rough overview of the universe that we're going to be exploring today. I wanted to go with this demonstration now. We'll switch to my other screen. Give me just a second here. All right, so hope everybody can see this. Is that, I'm not seeing the green arrow. Let me just share this again. Okay. What I've done here is if you go and open up HFSS and you go to File, Open Examples, this is a repository of examples that are very useful in terms of getting a good sense of, well, where's a template of something that I can just grab and use. And so what I've done here is within the HFSS folder, under examples, you have antennas, filters, metamaterials, etc. But under antennas, we have a number of different examples here. And so what I've done is I've picked the 3 different examples that are corresponding to the different antenna array examples that we just, the antenna array methods that we were talking about. So I've picked the phased array unit cell example here. I've picked the finite array multi-unit cell installed here and the finite array radome as well. So each of these examples are readily available within HFSS. You just open this up. You'll typically do a save as once it's open, so that, and you save it to a disk space area that's a working area that you have access to, and then open up these examples. So we'll start with the unit cell analysis here. Vivaldi. So this is an array here where we start with our, from a geometry perspective, we have a substrate, we have some PEC in terms of our feed, and then we specify the size of the airbox, and we specify some vacuum around our feed. And then on the perfect E, we have the equation for the Vivaldi surface is here. So I wanted you to be aware that you can, one of these options up here is this little F, and you can draw an equation-based curve as you're thinking about how you're creating geometry. We have this perfect sheet relative to our Vivaldi antenna. You can also use the HFSS antenna toolkit to pull some of these antenna, like a standard dipole and so forth are all available within the antenna toolkit as well. But when we're setting up a unit cell model, we start by setting up the unit cell, and basically we change the selection here from object to face, and then grab two opposing faces and right click, and we can assign boundary, and then under the boundary, we're going to do a coupled lattice pair. And you can also auto-identify lattice pairs. So if you have a standard box, HFSS does a pretty good job of just identifying the lattice pairs and setting up everything automatically. This is a big improvement compared to the sort of master-slave relationship we had probably a decade ago in terms of setup. And click on that, and you'll have your lattice pairs set up here. In terms of boundary conditions, we then have our perfect E boundary for the Vivaldi antenna. And then at the very bottom for our feed, of course, we want to do our input port here, port number 1. And then in this particular case for unit cell analysis, sometimes it's useful to do a Floquet port as opposed to radiation analysis at the top. And on our setup, when we specify this is at 4.5 gigahertz, but typically we'll be using the direct solver here for doing this kind of unit cell analysis. And then we run it, and we get our standard S parameter plot. And we can also start looking at the E fields here, or the surface currents as well. So this gets you started in terms of a unit cell analysis. And relative to the timing, if we go to our solution data here under the profile, this profile is a list of how the solver is solving as it goes through the solving process. So it starts off saying, okay, how many processors am I using, and what kind of memory do I have? And then when I'm doing the meshing, how many tetrahedrals am I meshing, and of what type, and how long does that take? And then it starts with the initial mesh, and then each adaptive pass. It shows you what its current status is on the adaptive pass and how much memory and time that's taking. In this case, it was 27 seconds for the adaptive passes to converge. And then we do the frequency sweep, and it shows you the frequency sweep as well. This, under solutions here, this tab under convergence is also useful to sort of show you, as the different passes happen, what our magnitude of delta S is and how close to finished we are and how many elements it's taking. And then, of course, we have mesh statistics here if you want to look at mesh as well. So these this solution area is something I can monitor as the solution is happening. And just wanted to show you that as well. Okay, so that is sort of the unit cell analysis. And if we shift now to a finite array, we start a finite array with a unit cell design. So in this particular case, we have somewhat similar. We've got our substrate here. We've got a Teflon radome piece here. We have our ports, and we have our just a perfect E antenna here. It's just a patch antenna with a ground underneath it. And similarly, we start by setting up the lattice pairs and specifying any PEC or ground metal here, specify our input and our flow K port, and we can kind of run it, and we're just kind of taking this as our initial patch. But now, from that individual patch, we might want to start creating an array that now is different from the initial unit cell. So we start by doing our unit cell analysis, maybe analyzing the unit cell for efficiency and initial radiation. But now we want to actually, okay, let's put that into finite array, start taking into account some of the edge effects, start looking at, well, if I have a radome on, and it differs on the sides and corners, what does that look like? And so you can sort of see here, we have now a 3D component array where we're only modeling 4 different pieces of this 8x8 matrix. And because we're only doing 4, that's 4 out of 64. It's a pretty big reduction in the amount of mesh needed to mesh this whole model. And so you get a huge reduction in time. Time needed to do this analysis. So to set this up, we start with each of these individual pieces. So we start with the patch, and I'm just going to go back to this original patch definition. And when we're doing this patch, we would basically set everything up. In this case, we've changed now the flow K port to a radiation boundary. You can't use a flow K port with this method in terms of the 3D component. And then with that change, we basically just select everything in the model here and right click, and then do create 3D component. And that takes all of this geometry, the ports, the boundaries, any mesh conditions that you might have set up, and lumps them all together as a 3D component entity, saves it as a particular file, and that file can then be used elsewhere. So I can just throw that this individual patch into any particular design, or I can, in this model here, I can insert it into, I can right click on model, create array here, just going to go to the properties if it's being already created, and then insert these unit cells here. And so the way to do that is you first create the 3D components. So each of these individual pieces, the patch that looks like this, we might have a radome side here, which is, in this case, we don't have any radiation, we don't have any radiators, any part of the patch, but we do have the side piece for the radome. We might have a corner piece for the radome, etc. So you take these individual pieces. One trick to this as well, though, is you have to make sure that these boxes are absolutely identical. If they're not absolutely identical down to the 0.0001 micron level, it won't, the periodicity won't fit together and it won't work. So definitely make sure when you're creating this geometry that those boxes are absolutely identical. And then go ahead and create this geometry, select it, do the create 3D component, save that. And then once we have all those 3D components, and we're now wanting to put them together in an array, you come to a blank HFSS hybrid modal network here. So we have with hybrids and arrays, it's important. And then right-click on 3D component, and you would browse 3D components, browse for those 3D component files you've already saved, and then add them to the model here. And so this one has 4 different components listed. Once we have those components listed, if you do model and create array, you can then start placing them into the design here. And you can see how we've placed the patch in this 4x4 pattern in the middle. We then have number 2 here is just a sort of a blank area with just some radome on top. Then we have this side piece that we were just doing here, 3. You notice it's got this little R here. It's rotated by 270 degrees. So it's, and then the other side is rotated 180 degrees. So we can change the rotation as we insert these. And then of course we have the corners. So we're specifying all the different pieces to the array using the 3D components, and those components can be different as long as they're both regular, regular pieces to each other. So that's how we set up this array. And then once we have the array, we can each of those patches, which has its own port, gets pulled in here, and then we can we have the individual. In this case, we have a 4x4, so we have 16 different inputs here, and then we can add these equations to help with phase shift and scan magnitude as a variable that allows us to change the beam forming and how it's formed. So in this case, we also can save to file and load from file. And sometimes it's easier to just take this and save it to Excel, then play with it in Excel in terms of creating these variable names and getting these formulas correct, and then saving it and then loading it from file here as well. So that's another trick in terms of setting this up. Let's see, and then you can always go, once you've added these 3D components, as I've shown you here, you can edit definition and jump back into it. So if you need to change something as well, you can change it sort of on the fly as well. And then, so that's our excitations. And then we have our standard setup in terms of analysis, where we do our sweep and so forth. And in this particular case, you can also choose to use direct solver or domain decomposition, depending on how large your model is. And you may want to play with both of these options to see which one runs faster for your particular model. Domain decomposition will tend to go much better for much larger stuff, clearly, but if you have something that's sort of tractable within the direct solver, it can definitely be faster. So you want to explore that as well. And click on this skip 3D component array solve during adaptive passes can also speed things up as well. So then we have our analysis, and then we can get our standard gain plots here in the different orientations, or from a 3D perspective to take a look at what's going on with our antenna. This array can also be used. So our 4x4 array can now also be used within a larger environment. So now we've designed the antenna and optimized its gain, but now we want to actually look at its performance in its environment. So there might be metal around nearby that will affect the performance of this antenna, and we can compare and contrast that. So this is the satellite here, where we've taken this antenna and imported it where you create an antenna and link to source design. So we've got the design modeled as the antenna here. In this case, we're linking to the source design as a for the near field output to then run an SBR analysis to again, model that antenna with in its environment. And so you can see here, the gain plot here definitely changed when we went from one, without, oops, sorry, this one here. So this is without any metal around it. And this is, whoops. This is with those arrays and other metal around it. You can see how the gain has changed. And the antenna performance has changed. So think about using SBR Plus in that way in terms of modeling what your antenna performance is in the environment you're in. And this finite array multi-unit cell installed model is a good sort of template for how to do that. So there's a second finite array radome model here, which is a 2x2, somewhat similar, slightly different patch array model here, and they've modeled it explicitly. And then on the array side, for this multi-cell array, they've taken a slightly different view, slightly different visualization of the array here, but pretty similar. And this is, still a 4x4 here. Sorry, yeah, 4x4. And one of the differences here, though, is now they've used, well, this was direct solver, but you can use domain decomposition. I think, yeah, it's a pretty similar model. I guess it's just a slightly different radome shape and how they've done it here, and they've got some different outputs in terms of S parameters and so forth. Yeah. So that was kind of the demonstration. Just wanted to sort of show you where these models are in terms of using them. And now I'm going to switch back to our slides. Okay. So when we think about the speed up that we can get from this, if we just look at sort of an explicit analysis, maybe taking 4 hours, this finite array DDM can take 24 minutes, so a really huge speed up in terms of time. And you can see the RAM goes way down as well. And you can see the results between the two are pretty darn similar in terms of our results. This is just sort of a mathematical analysis on the unit array analysis side, where we're neglecting edge effects in terms of that. Finite array domain decomposition. This is just sort of showing how it works, basically, where we have a converged mesh from the unit cell that's duplicated for each element, and that makes it much more efficient and faster. And then on the 3D component side, there's a little bit more setup time to create those 3D components. Make sure those bounding boxes are absolutely identical and set up the lattice pairs. But once we have all this, it's much easier to share designs, move them around, move these 3D components around, and change up how you're doing your different designs. So that's another advantage on the 3D component side. And as we were just showing, this is kind of another look at our antenna mask layer and how that's set up. And another advantage of the 3D components is that we can, when we save it as a 3D component, we can also save it as an encrypted file. And so that's great for vendors who have, say, antenna pieces where they want to enable you to use that antenna within your designs. Say similar to that SBR analysis we just went over, but they don't want their design is proprietary, so they can share the encrypted model, hide the internals to the model so that you don't see the geometry, you just see the block and its output, and still enable you to use it use it and reuse it in your designs. So that's another advantage here for 3D components. As I mentioned, that all of this is done in parallel. So the other important advantage in terms of meshing is each of these three different pieces can now be meshed in parallel and computed in parallel. And so this method of doing it this way, as opposed to explicit, enables you to utilize your HPC much more effectively. So you get a bigger speed boost using HPC when you use this 3D component methodology, because it lends itself to parallelization much easier, faster, and better. And as we went over, you want to draw the unit cell and have your lattice pair coupled, and apply right-click to create the 3D component. And that's it. I just wanted to mention a few other tricks here. If you place your 3D components in the user library, you then, by right-clicking on View Component Libraries, you'll have access to those 3D components as a right-click, and you can just drag and drop them and reuse them in your design. So if you have a 3D component that you're planning to use in lots of different designs, sticking it in the user library is a great way to access it, use it, make it more friendly. And to access that, you want to, or find that location, you just go to this Tools, Options, General Directories in AEDT to get the user library location, so that you can know where to place those 3D component parts. Another option that will save you some time is if you are just interested in the radiated fields only, as opposed to viewing the electromagnetic field patterns directly, you can check this box in the advanced save option, the advanced solution setup options, and save radiated fields, and that will save you a huge amount of disk space. So you notice when I'm saving the fields, it's got to spend time disk writing, so it takes a little bit of extra time as well. But we can go from using up a huge amount of disk space to saving the fields to a much smaller amount, and save a lot of disk space here. And another option I wanted to mention in terms of saving time is if you're only interested in one excitation type. So in other words, if I have I'm looking at when I edit my sources and I only have one, I only want to like source it from the center and in one particular direction. I may not want to, I can use this composite excitation where it reduces the amount of computation required. So normally HFSS, when you run a network analysis, it's solving every possible excitation. With composite excitation, you specify a single excitation and it runs that analysis for that single excitation, but it doesn't do all the rest. And as you can see, you can get a much larger 9 times, 41 times, especially for the larger types of finite antennas. If you're just interested in that one single excitation, you might be interested in like 4 or 5, and so then you might have 4 or 5 different input excitations and run it 4 times, but that still might be a lot faster than running every possible excitation using a network analysis. So I wanted you to be aware of that. If you're looking for more information, just use the help and do look up composite excitation. And so now I guess I want to just pause and ask anybody if they've got any questions. Okay, so with that, just wanted to say HFSS can efficiently, as in computationally efficiently, solve your complicated antenna designs. And we'll conclude with a couple of additional resources here. Within the ANSYS Learning Hub, there's a HFSS Getting Started Learning Room if you're new to HFSS. There's an antenna and microwave learning room if you're interested in antennas and microwave structures. And then an antenna array and periodic structures course that dives a little bit more into these examples in terms of setup and kind of gives you a step-by-step directions in terms of running these analyses. So please take advantage of that course as well. And then a few other resources are, of course, email us at support@ketiv.com or call us if you're running into issues or need some help there. There's a YouTube channel on how-to that has a lot of YouTube videos if that's another way you learn. There's a webinar resource center that has different webinars, maybe more particular to your situation, that are very interesting. And finally, in the innovation space, there are free courses as well. This is sort of tends to be geared more towards students, but certainly there's some interesting stuff in there beyond the ANSYS Learning Hub resources as well. So just wanted you to be aware of these resources as you're getting started and going. And then also, if you're interested, if you don't have capacity or if you're interested in some help, in addition to supporting customers, we also do the work ourselves in terms of simulation. So if you're interested in having us do the simulations for you, we do take on consulting work for simulation services in these areas, mechanical, fluids, and electronics. Please keep that in mind if you're need some extra surge capacity, are unfamiliar with a particular type of physics and want some help there just getting started, and we can use this sort of service engagements as a training platform to get you launched into it as well. Kind of you do it 100%, we do 100%, and anywhere in between in terms of our training. So please do keep us in mind relative to services. And that is our conclusion.
Thank you so much, Graham, and thank you to everybody for joining. We will see you guys next week.